Good morning. This video I'm going to look at some of the ideas for the RF amplifier that's going to be sitting straight after the antenna to boost that incoming signal. I'm going to base it around a Class A common emitter amplifier using the 2N3904, nice common little transistor there. Thinking there is to have just straight out capacitor coupling coming in, and then the output will use a transformer based on the FT37-43 little toroid there. So that's the idea. I'm going to do two versions which I'm going to simulate using LTSpice, and then pick one to solder up and then do some actual physical testing with the SIGGEN. So the two versions I want to look at is one with a quiescent emitter of 5 milliamps, and the second one will be 10 milliamps. I don't want to go too much more than that, just want to sort of keep the current draw down, noting that we're looking at one RF amplifier, two IF amplifiers, and the AF amplifier on receive. And if I can get the total of all of those to be, say, less than 100 milliamps, then that's what I'm sort of guessing. I must admit, I don't know if that's actually a good figure for portable radios, but it's an aim point anyway, so I'll be curious to know what others have done with their radios for portable radios, just to see if it's in the ballpark or not. I did play around last night with a version down to just on 1.5 milliamps. I did that version based on the characteristic curves for the 2N3904. And just notionally selected. I wanted the maximum of 10 milliamps possible on the collector, using 12 volts. So for cutoff, that would have gone up to 12 volts there, and then selected in terms of the middle of the linear region a base current of 35 microamps, and then using that as the start point, designed up a radio, or an amplifier I should say, based on, like I say, that 35 microamps, and just playing around, and that came down to a quiescent current of 1.5 milliamps, and then just played around with the load, the impedance ratio here to present gradually higher and higher loads on the collector to change the overall gain of that stage. Interesting project, but for this one here, for the exercise today, is to just look at that 5 milliamps version versus the 10 milliamp version, select one to solder up. So based on that, so here's a separate page. So the maths for working out the emitter resistor and the two biasing resistors is the same that we've seen. Same sorts of rule of thumb. We're going to, for the operating beta, so the beta at their operating frequency of 7 megahertz, we take the gain bandwidth product for the 2N3904, which is 300, so 300 divided by 7 gives us a Beta.AC of 42. For the first one, we'll let IE equal 5 milliamps, and now we can proceed. And the other rule of thumb, making our emitter voltage a tenth of VCC. So 1/10 times 12 divided by 5 milliamps flowing through it, gives us from Ohm's law 240. So our nearest standard value will use 220 ohms. For R2, just recalling, that's our lower resistor here. That has 10 times the base current going through it, and this one has 11 to make this a nice stiff voltage divider biasing for that. So looking at R2 here, it's our emitter voltage plus 0.7 divided by 10 times our base current. So base current is our collector current, which is approximately equal to our emitter current. So 5 milliamps divided by 42. Do the division, comes out at 1595, so we'll use 1.5k. For R1, the top resistor, that's now going to be, again straight Ohm's law, 12 volts minus the voltage here divided by the current through it. So 12 volts minus 1.9, if you recall, that's our emitter voltage plus 0.7 divided by 11 times our base current, gives us 7712, so we'll use 8200. Exactly the same process for the 10 milliamp version. So I won't go through it here, but just substituting in 10 milliamps where appropriate to come up with our three values for those particular resistors. Right, for our input capacity here, different rules of thumb there. One option is it should be well less than 100 ohms. Other rules of thumb should be less than 1/10 times Rin, and I'm pretty happy with the filtering. Oh, I'll go into that. Anyway, so let's run with less than at least 1/10 of Rin, where Rin equals R1 in parallel with R2 in parallel with Re, of which Re equals little re plus large Re, which is our external resistor, the unbypassed portion. This is fully bypassed by CE, so we're only now looking at little Re, and recalling little Re equals 26 divided by IE in milliamps. So from that we can substitute our values in for both the 5 milliamp version and the 10 milliamp version, and we come out respectively for Rin of 5.17 ohms and 2.59 ohms. Right, so if we were to pick on a value that quite often gets used for RF circuits of 100 nanofarads, and we know that our capacitive reactance is 1 over 2 pi Fc, we can substitute in 1 over 2 pi 7 megahertz times 100 nanofarads equals 0.227 ohms. So that's certainly less than 1/10 of our input resistance, and it's also certainly well less than 100 ohms. So we'll stick with that, happy with that one. Now the output transformer here, that's going to be transforming 50 ohms. Of course, following this is going to be, I think I'm going to go with the antenna to a bandpass filter to this amplifier to the ADE1, as opposed to the antenna coming into the amplifier and then into the bandpass filter. Either way, it doesn't really matter. The load on this particular amplifier is going to be 50 ohms. So I need to transform 50 ohms back to our rule of thumb for this particular amplifier is 200. So we want to present 200 ohms to the collector of that transistor. So I want to see 200 ohms there. So two ways of doing that. So that's a ratio of 4. So 4 times 50 equals 200. So one way is to use a 10-turn bifilar transformer on a FT37-43. So that would transform that low impedance here to that high impedance there. Or I can run with what I've been sort of doing more traditionally, or more often than not I should say, is just using a sort of straight out transformer with a primary and a secondary. In that particular case, so looking back this way, 50 times n squared equals 200, so there we can work out n then equals 2. So that's going to be our turns ratio. And the other rule of thumb here is we need to make sure that the smaller winding, which will be on this side, needs to be, and you see different figures quoted around, so 4 to 5 times the load impedance. So 4 to 5, so let's say a minimum of 4, so 4 5s are 200. So this, the inductive reactance of that small winding there needs to be at least 200 ohms at our frequency, or the lowest frequency of operation. In this particular case it's going to be 7 megahertz. So what we can do, we know that XL, our inductive reactance, equals 2 pi FL, so therefore we can solve for the inductance we're after. So 4 times 50, which we just sort of set up here, divided by 2 pi 7 megahertz, we get a minimum inductance of 4.5, so again 4.547 microhenries. Using the online calculator for an FT37-43, 4 turns, a nice round number there, will give us 5.6 microhenries, which will equate to, if we now substitute back into here, at 7 megahertz gives us 246 ohms. So that's good. So that's sort of in that sort of ballpark. It's a minimum of 200. Noting too that 5 5s are 25, which is pretty close to that. So we're getting pretty close to even 5 times our load impedance. So that's good. Big tick there. So that now tells us we've got 4 turns here, and we worked out up here that we need to have a turns ratio of 2. So 4 times 2 equals 8. So it's going to be 4 turns on this side and 8 turns on this side. And I've just written up here, when we go into LTSpice, and we'll have a look at the transformers. Transformers are simulated by using their inductance. So you don't use turns, you use inductance. So 4 turns gives us 5.6, and 8 turns gives us 22.4 microhenries for an FT37-43. So in the LTSpice, that's what you'll see there for the 2 transformers. This one here will be 22.4, this one will be 5.6, and we have to give a coupling coefficient, which typically we'll use 1, which is 100%. A little bit unrealistic, but for the sake of the simulation, that'll be fine. So let's break here, we'll have a look at the simulation, and then after that we'll look at actually soldering it up. So here are the 2 amplifiers being simulated in LTSpice. On the left hand side here we have the 5 milliamp amplifier, and on the right hand side we have the 10 milliamp amplifier. So on the left hand side here, if I was to hover over the emitter resistor, we can see down the bottom there it's roughly 5.7, so again 5.1 milliamps. The input here, notionally the antenna, I have a 7050 kilohertz signal coming in at 1 microvolt, and we are scoping the output across our 50 ohm load. So there we're getting roughly, for 1 millivolt in, we're getting, if I was to hover down here, we're getting at roughly 16.62 microvolts out. So 16.6 over 1 equals 16.6. 20 log that gives us around 24 dB. For the 10 milliamp version, we're getting there roughly 28.6 microvolts out for 1 microvolt in, which gives us roughly 29 dB. Now let's go back to that one. Let's say we increased our voltage at the antenna from 1 microvolt. Let's go up, say 60 dB, and we'll make that 1 millivolt. And we'll do the same for the 10 milliamp version. So we'll make that 1 millivolt, and we'll simulate that. And we'll simulate the other side. So now we can see there on both sides we're up into, for 1 millivolt in, we're getting for the 5 milliamp version roughly sort of 17 odd millivolts out, and still nice and linear. And same for the 10 milliamp version, getting up there to around that sort of 28 millivolts out, and again still nice and linear. So that's good. If we were to look at the frequency response, so let's change our, let's go to an AC analysis. Let's go for an octave, we'll go for 1000 points. Let's start at 1 meg, 1, 2, 3, 4, 5, 6, and we'll go to 30 megs, 1, 2, 3, 4, 5, 6, and we'll just copy that and do it the other side, control copy, okay. Let's do that for the other amplifier, AC analysis, control V, paste. Right, let's simulate that one, and let's simulate this side here as well. So we're now looking at the frequency response from 1 megahertz through to 30 for both amplifiers. And we can see there that if we were to pick on the 5 milliamp version, we're sort of getting our max peak there, if I was to hover over that, at roughly 4.9 megahertz. But going up, just creeping along there to sort of just on 7, we're still getting our sort of 24 dB, which is what we saw with using 20 log V out over V in. So that's to be expected. But still, more than happy, even though the maximum gain is a couple of megs down, for our area of operation 7 megs, it's still plenty of gain for for boosting up that antenna signal, and arguably we'll have to attenuate that a little bit. And again, on the right hand side, the 10 milliamp version. Again, our maximum gain is around that sort of 3.8 megahertz, so the top of the 80 meter band. But again, if we go creep up there to 7 megs, which is roughly there, we're getting what we expected from our straight V out of a VM of 29 odd dB. So again, even though it's not optimized for the 40 meter band, still plenty of gain, so I'm not going to worry too much about that, trying to twig any other parameters. So at this stage of the game, I'm going to stick with the 5 milliamp version, only because the performance seems to be quite similar, both linear, but obviously having a lower current drain on the battery gives longer endurance. Now, if my maths is correct, that's a 6,000 milliampere hour battery. So at 10 milliamps, it would be 60 hours of receive off that battery. And obviously, if I'm drawing 5 milliamps, I'll get 120 hours. But either way, I'm going to now solder up the 5 milliamp version, and we'll see how that goes. Actually, putting some proper signals into it and using the O-scope. For interest's sake, I did some other experiments with the simulator, playing around with, we look at this 5 milliamp version here, with the 8 turn or the collector turns ratio. So that's currently sitting on 8 turns, presenting 200 ohms to the collector. And what I was playing around with is just increasing that turns ratio up to 11 and 12 to present a higher resistance to the collector to increase the gain. It was just purely for interest's sake, but I've gone back to just sticking with that 8 turns to 4 turns to present that sort of rule of thumb 200 ohms, and then just using the emitter current to reduce little re to affect the overall gain of that stage, bearing in mind that the voltage gain for this particular amplifier here is approximated by our collector load divided by Re. In this case, it's going to be little Re because the large external resistor is fully bypassed by their 100 nanofarad capacitor. Anyway, let's break here, let's solder it up, and then we'll have a look at how it performs. Right, so we've got the circuit soldered up, just using again strip board there, sitting on just a copper backplane. You'll see dotted around the place, the tracks being cut here and there just to minimize any kind of feedback across those tracks. Sort of quite conscious that at the higher frequencies you can get that capacitance between the tracks. So what I try and do wherever I can is cut them in half and break them where I don't need them, just to stop those signals getting back in any kind of inter-track capacitance. Anyway, so we've got the yellow wire here is the input through our input coupling capacitor into the transistor itself. There goes our output transformer. The red windings are the primary on the collector side, and the green ones are the secondary on the 50 ohm. That's a 51 ohm resistor, so close enough to 50 ohms. And just in terms of the overall configuration, we have, let me just move the camera back a little bit, got our SIG gen on the left hand side. It's not the best one in the world, but it's all I've got to use at the moment. So that's currently set up on 7.025 megs with 10 millivolts. That's feeding in, as we said, into our amplifier, and on the output we've got the oscilloscope. Channel 1, which is the top trace, that's our input, and then channel 2 is our output, and that's both on the same settings, of 50 millivolts per division. So for a comparison there. Something I didn't mention in LTSpice, we're just looking at the power dissipation. So LTSpice was telling me that for that transistor I was going to be dissipating around 56 milliwatts that was based on 5 milliamps, and that's well within our allowable 625 milliwatts for that particular device. So now that we've actually got the amplifier built up, soldered on the board, using real world components with the tolerances they have and the like, same with that particular device. Not unusual, certainly from my experience here, and like I say, I'm not an expert in any way, shape or form, but I find the LTSpice is good to give you a bit of an idea of where the circuit's going, and when you do actually solder it up, there are some variations between what you simulate and versus what you actually have in for real. So for example here, this circuit here is now drawing 6.4 milliamps DC, which is good, that's fine. That's pretty close to that sort of 5 milliamps that the maths was around, and certainly well within that 10 milliamps which I wanted to stick well and true within. So what I might try and do here is we'll just look at the output waveform. That's the bottom trace there, and we'll vary the frequency above and below that 7 megahertz just to see the effect of that. So that's currently on 7.025. So we start to drop it down in frequency. We're now down to 654, and if you remember in our LTSpice we had that that curve where the peak was roughly around that sort of 7 megs. So that's not unusual to see that starting to drop off now, and then up to 7, 8, 9, 10, and then starting to drop off again. So I think around where we are, which is sort of around there, that's 9, that's 7, I think that's not too bad. So that's sort of approximately in line with what we saw with LTSpice. Like I say, 10 millivolts there. We can go up to 20, 30, 40. I'm still keeping quite, wrong one, output. Still keeping quite linear there. That's 50 millivolts. So I think that's going to be fine in terms of what we're potentially going to see coming in through the antenna. Unfortunately, I can't go any lower than the 10 millivolts here. I don't have a good attenuator. I've got this one here, but it doesn't perform overly well. I find quite often that it tends to distort the output. Certainly once you get above sort of 20 dB, so I find that a little bit annoying, especially when you're trying to see if you've got any kind of nonlinearities being introduced. It doesn't help when your attenuators introduce that in the first place. Anyway, so I won't go on any further. So at this stage of the game I'm going to lock that in, so to speak. I'm quite happy with that in terms of the current draw. I get the impression that the gain's about right. I did do some measurements before, and the amplifier is producing 22.4 dB. So that's quite close to what we were expecting in the simulation. So I'm quite happy with that, and just noting too that when this was put together, it wasn't designed to produce a specific gain. It was more just produced, and then we'll see what gain it produces, if that makes sense. It's sort of a backwards way of doing it, but I was quite happy to do that for this particular amplifier. Anyway, I don't think there's anything more to talk about. I think at this stage of the game, probably look at the mixers next, and then we'll see if we can get it either, just thinking about either potentially a direct conversion receiver going, or go straight into that sort of single conversion superhet with those two ADE ones. So I think that's what we'll probably do at this stage of the game, put some thought to that. Anyway, 73's all, and hopefully, fingers crossed, there was something useful in this video. Cheers all.